n and m, if they are distinct, then their successors are also distinct. Okay, so this is a new axiom. And this axiom, what does it say? It says that if we have distinct natural numbers, then their successors, the ones which appear next to them, are also distinct. Now, if you recall the things we did in while we studied logic, mathematical logic, there we came across implications, right? P implies Q. So this is a statement like that, where this is the hypothesis and this is the conclusion. And there we have come to know that an implication is logically equivalent to its contrapositive. An implication and its contrapositive are logically one and the same. So if we write the contrapositive of this implication, it will look like this. Or equivalently, this is P, this is Q. P implies Q is equivalent to negation of Q implies negation of P. Negation of Q is the successors being equal implies negation of P is the elements being equal. So either you can use this or you can use this. So this is a new axiom. Now how does this axiom prevent this sort of things from happening? So let's just see that with a proposition, of course. So this will be proposition 218. And what this proposition says, 6 is not equal to 2. Okay, this is just one of the problems that is taken care of by this axiom. All of these things can be shown to not occur if we assume this axiom. So this is just one of them, because you see here 5 is equal to 1 and we will have 6 equal to 2 in this first number system. So now we show that cannot happen. So let's look at the proof. The starting is similar to the ones we have already seen. Suppose 6 is equal to 2. Then, okay, what is 6? By definition, what is 6? 6 is the successor of 5 and 2 is the successor of 1. So if we look at this, and so by repeated application of axiom 2.4, we have, what shall we have? We have 5 plus plus equal to 1 plus plus. So now we have 5 equal to 1, which implies 5, what is 5? 5 is the successor of 4 and 1 is the successor of 0. So again we are applying axiom 2.4 and that gives us 4 is equal to 0. And And this contradicts, I think, one of the previous things that we have already proved. But this is a contradiction, but this contradicts proposition what is the proposition number? I have forgotten the number. Let me just quickly see what it was. 214, so it will be 216, I think. Yes, proposition 216. Okay, so our supposition is wrong. Okay, so that's how we have gotten rid of that problem from the previous example. Now, now there are 4 axioms. The first one says that 0 is a natural number. The second one says that the successor of every natural number is a natural number. The third one says that 0 is not the successor of any natural number. And the fourth one says that distinct natural numbers have distinct successors. So now it seems that we can keep the natural numbers distinct, that is, these numbers, now none of them will be equal to any other. These are all distinct. Of course, we have only shown that 6 is not equal to 2 or 4 is not equal to 0, but it can be shown in general using these axioms that no two natural numbers are equal. In fact, this proof gives you an idea of how to achieve that. You consider two natural numbers m and n, right? And then you keep on using axiom 2.4. If you assume they are equal, at some stage you will see that some natural number which is not equal to 0 it becomes equal to 0. Or at some stage you will have something like this, k plus plus is equal to 0. So that will contradict the third axiom and the proof will be over. So we have now made the natural numbers distinct. So far everything seems good, but there is still one more problem. And this is a peculiar problem. So that problem will be explored in this next example. Example 219. Now this example is informal. When you see the word informal somewhere, it means that we are in that item we are using something which we have not defined yet. So the thing is informal in the sense that we are going to use something called integers and half integers. Suppose the system of natural numbers consists of the following integers. We have not defined integers yet. It will come only after we have constructed the natural number systems. But anyway, we use this word, so that's why it's informal. Integers and half integers. 0, 0.5, 1, 1.5, 2, 2.5, and it goes like that. Now the challenger has produced a new example, new problem. And now he has come back strong because this seems to be a peculiar thing. You see, first of all, we go the usual way. Let's just, I have not written what the incrementation operation does. It's usual. 0 plus plus is 1, successor of 1 is 2, successor of 2 is 3, etc. But at the same time, now I have some additional problematic elements and they have successors too. This is 1.5, 2.5, etc. That's how the successor function behaves. Now let's go the usual way and check whether the 4 axioms we have now are satisfied by this system. 0 is a natural number, it's there in the system. So axiom 1 is true. The successor of every element in this system is again an element in this system. Successor of integers are of course integers, but the successors of these fractional numbers are also there. Okay, so if we are saying that these are all the natural numbers, then the successor of even these strange looking numbers are also there, which means they are also natural numbers. From our prior knowledge, we know that they are not going to be natural numbers, but because we don't have any prior knowledge now, so the second axiom is true. The successor of every natural number is again a natural number. What is the third axiom? 0 is not the successor of any element. That is also true here. In these equations, 0 appears nowhere on the right hand side. In none of these equations, it appears on the right hand side. So axiom 3 is also true. What is axiom 4? Distinct natural numbers have distinct successors. That is also clearly true here. Distinct natural numbers are distinct successors, have distinct successors. So again there is a problem. And this problem is somewhat strange and is a little bit different from the previous problems. In the previous problems, what we had is that we were somehow trying to make these symbols distinct. Okay, but now the problem is that some rogue elements have entered the system. These are like viruses. We don't need them. They are unnecessary elements, but nevertheless, the axioms that we have had so far, they don't chuck them out. They don't prevent this from happening. So something else is needed. Now this, however, is very difficult. Okay, people were not able to come up with anything for a long time, but ultimately one ingenious solution was given, and that solution, you already know this, fifth axiom, is another axiom, of course. Principle of mathematical induction. Okay, the fifth axiom is the axiom which states the principle of mathematical induction. That is also an assumption. Now, why this fifth axiom, or how this fifth axiom prevents this sort of things from happening, we will see that. But let's just take the statement which you already know. We have discussed and we have in fact used the principle of mathematical induction in solving many problems. But let us just state, let Pn be a property pertaining to the natural number n. So, although we have in our study of mathematical logic, we have seen what Pn is. It's a statement which involves n. The true definition of a property in a strict logical sense is somewhat more difficult, and we don't need that actually. The working knowledge of what Pn can be is enough for us. So let's just take some examples. Example means not an example in the sense of the text, but some example to clarify what Pn is. Pn can be any of these statements. N is even, n square plus 1 is greater than 0, n plus 2 is odd. Things like this. Okay, statements involving n. Statements you already know by now are assertions, so which are either true or false. Now so these are statements involving variables. So, and they have been restricted. These variables have been restricted. N is a variable, it has to be even. So for some particular value of n, say if you take n equal to 1, then this statement is false. If you take n equal to 2, this statement is true. This statement, the second one, is always true. For every natural number, n square plus 1 is always positive. The third one, n plus 2 is odd. For that, n has to be odd. So for all odd natural numbers n, this is true. If n is even, then this is false. That's what Pn means. Okay, now such a Pn is given to us, some property pertaining to the natural number n. Now there is a restriction. If P of 0 is true, you know what it is. And P of the successor of n is true. See, we will be tempted to write Pn plus 1, but there is no plus available to us yet. We have not defined addition, so we are going to use only what we have. Pn plus 1 is true whenever Pn is true. So these are just the basis and the induction hypothesis. Then Pn is true for all natural numbers. N. So this is just again writing what we already know, but in an axiom form. This is also an assumption that we have made along with the other 4 assumptions. Okay. Now, excuse me. So this is the 6th one. Okay, so now there is a remark that can be made or that should be made on this axiom. That is the remark 2.1.10. That's 2.1.10 because the 9th item was that problematic number system where we had half integers. So what this remark says, oh, this is about that thing, property. The use of this word here. Okay. Now, I have already said what property means, what it can be. But in this remark, there is a logical remark. And that logical remark is that instead of calling axiom 5 an axiom, actually it should be called an axiom schema, which is slightly different from an axiom. The difference of this one from the previous ones is that it not only puts restriction on variables, but restrictions on properties involving variables. You see, in the other axioms, in the first axiom, we have no variable. 0 is a natural number, so it has only a constant. Okay, on that we have put a restriction. In the second one, we have a variable n. Whenever n is a natural number, its successor is also a natural number. So on that variable, we have put restriction. In the third one, also there is variable. No n has its successor equal to 0. Similarly, the fourth one also has variable, but the fifth one has variable, but it has properties also involving that variable. If you restrict properties, then you get something called axiom schema. It's not a single axiom, but it's a template for producing infinitely many axioms. This, however, is a remark that is of more interest to logicians than mathematicians. And if we want to discuss the distinction between an axiom and axiom schema further, then that is well beyond our scope. Okay, that lies in the realm of logic, not mathematics properly. So that is one thing that has been remarked here. Okay, now what is the intuition behind this axiom? Okay, why has someone come up with this axiom in the first place? So the intuition behind axiom 2, 5, it is just simply this. You see, we say that P of 0 is true. Okay?